Hello everyone, I welcome you all for this video session on fast decoupled load flow method. Let us see the objectives of this video session. So in this video session we are going to see the first understanding of the basic decoupled load flow method and analyzing the advantages of fast decoupled load flow method compared to previous Gauss-Seidel and Newton-Raphson method. And finally, we'll compare all the methods in different aspects. So when you see the decoupled method, before going to the first decoupled method in 1973, the decoupled method is introduced. So the basic concept of decoupled method, if we understand any practical electrical power system in steady state condition, there is a strong dependence between among the four variables which are defined in the power system. When we see the four variables in the power system when we are solving the load flow solutions are: one is active power, which are the real power; reactive power Q; bus voltage angle delta; and burst voltage magnitude V. So when we observe the practical electrical power system, there is a strong relation between these four variables. So one of the strongest relation is real power and the load angle, reactive power and the bus voltage magnitude. So based on these strong relations, the decoupled method has given some simplification on NR method. It is just extension to the NR method, but some part of the simplification is given because of this strong relation and weak relations. So when you see the strong relations in these conditions, in realistic steady state condition of the power system, active power and load angle, which are the strongest relation between these two parameters, and reactive power and bus voltage are the strongest relation between these two parameters. So let us see the explanation of that. So how the active power and load angle are which are dependent each other, which are the strongest relation. When you are seeing the power angle curve in the power system, so when angle varies, obviously the active power value will be varied. So where the equation of active power is equals to EV sine delta. So here the XS is constant, this value is constant because it's the P max, the value of this one, this is the constant because of the prefixed values of the voltages and reactance value of the transmission line. So this value P max is constant, your active power is directly depends upon delta. So the voltage, it depends on voltage, is a very weak relation. Now that is the first relation, the strongest relation between the real power and delta. So when delta varies, P will be the strongest relation. So another strongest relation in the power system is the reactive power Q and bus voltage magnitude V. So this is the one of the important relation in the power system. So let us see the voltage control concept in the power system. So when you are considering a generating station and sending end voltage V1 and receiving end voltage V2, and the reactance X and the power flow between the sending end to receiving end is P plus JQ, and a load is connected. Then if we analyze this receiving end voltage V2, so that V2 can be derived as V1 minus J P minus JQ divided with V1X. So when you see the direct equation, the receiving end voltage is component, the reactive power component is directly subtracting your sending end voltage to get a receiving end voltage. So it directly influencing on your receiving end voltage. The V2 parameter is directly decreasing with the value of Q. So that means the Q and voltage, bus voltage, both are more voltage magnitude, both are more dependent than load angle. So another strongest relation is reactive power and bus voltage. When you say the real power and bus voltage magnitude, there is no importance when you change the bus voltage magnitude, because the bus voltage magnitude is very restricted to change. So it's only depends on reactive power. So it will not depends on that much of relation is not there between the active power and bus voltage. So similarly, there is a weak relation between the reactive power and load angle. There is no much variation between the load angle and reactive power. Therefore, by considering the strong relations between the active power and load angle, reactive power and voltage, so we can retrieve back the characteristic equation of the Newton-Raphson method, the delta P and delta Q, and the Jacobian matrix H, N, M, L, and change in load angle and change in voltage. So therefore, the half of the elements of the Jacobian matrix represent the weak coupling. So how we are seeing, how it will be, we will see. So H is the relation between the change in P and change in delta. Element N is the relation between the change in P and change in voltage. Similarly, element M is the relation between the change in Q and change in delta, and element L is the relation between change in Q and change in delta. Now see, H is the relation between P and delta, which is a strong relation. N is the relation between the change in P and voltage, so which is a very weak relation. So M is the relation between change delta Q and delta, then it is a strong relation, and L is the relation between Q and V, it is a strong relation. So based on this, so after assumptions between the strong relations and weak relations, so we can neglect the N and M, which are the weak coupled elements, Jacobian weak coupled elements, N and M. We can consider these elements of the matrix, submatrix 0. Then your matrix will be, after assumption, which will be rewritten as your characteristic equations. So change in P, H, delta, change in Q, L, mod V by V, you can consider this is standard notation of that. So where it can be shown as your H submatrix Hij and Lij after substituting this. So your Hij, Lij value, it is a Vi, Vj, Cij sin delta Ij minus Bij cos delta Ij. So this is the equation we already derived in Newton-Raphson method. Similarly, Hii value minus Bii mod Vi square Qi, and Lii value it is a mod Bii mod Vi square plus Qi. So this is the off diagonal element, these are the diagonal elements of the matrix, submatrix H and L. Now after that, still with the decoupled method, only these two elements will become 0, but we have to find out the Jacobian matrix again. Still complexity, the speed of the matrix will be the same. So again with further advantages, because there is not much of an advantage from the point of the speed by using the DLF method. There are certain physical justifiable simplifications still we can assume to make the process very speed. So that assumptions if you are assuming, and then that method will be called as fast decoupled method. Still we are assuming some more assumptions to make it your decoupled method very fast. So that's why it's called fast decoupled method. So it is also be introduced by the same scientist. So in 1974, with a 1 year gap, he introduced that one. So what are the assumptions we'll see in the fast decoupled method? We'll see. So first assumption is, because when you observe in the practical power system, the operating delta angle is very low value. It's a very low value. So we can observe from the power angle curve, it's a very low value. We can observe delta will be operated with the lesser values of the delta. So we cannot go nearer to the pi by 2 because of the stability condition, where we will get a critical stable condition. So we'll assume the delta is a very low value. Once the delta is low, cos delta is approximately equal to 1, and inversion of that, sin delta Ij value is approximately equal to 0. So with these two assumptions, so with that lower value of the delta, cos delta Ij will become equal to 1, and sin delta value will be approximately equal to 0. So with these two assumptions, if you substitute, then your terms Gij cos delta Ij is much lesser than Bij, and second term Qi is much less than Bii mod Vi square. So these two terms will be, why these two terms we are considering, because these are the calculation of H and L terms. Now with the consideration of these fast decoupled assumptions, the entries of H and L submatrix will become considerably simplified. So your Hij and Lij values will become minus mod Vi mod Vj Bij, where I is not equals to J, and HII, that is a diagonal element of H and L, that is a minus BII VI square. So, but then your equation will become delta P is equals to substituting this. So, VI Vj and Bij dash is nothing but minus Bij into change in load angle. Similarly, delta Q is equals to Vi Vj Bij double dash minus of this one will become mod V by mod V. So, these two are only the equations we have to solve in the first decoupled method. So, where Bij dash and Bij double dash are the elements of minus B matrix. Now, further decoupled method, a logical simplification of further decoupled load flow method algorithm can be achieved by, so omitting the B dash, omitting from the B dash the representation of those network elements that predominantly affect the reactive power flows. So we can still omit some part of the B dash matrix to make it a more sparsity, get a more sparsity to the B dash matrix. So shunt reactances and transformer off nominal in phase steps we can neglect, so that your B dash matrix simplification will be very fast. And again, another thing is neglecting from the B double dash the angle shifting effects of phase shifters. So that is another part we can consider in B double dash matter. And the third one, dividing the two FDLF equations, what delta P and delta Q equations, with mod Vi and setting Vj value is 1 per unit, so that we can further simplify our equations. And the fourth assumption we can take, ignoring the series reactances in calculating the elements of Ba dash, which then becomes the DC approximation of power flow matrix. So with these four assumptions, what advantage we will gain? The first advantage, your B matrix will become more and more constant and more sparsity. It is very easy to calculate, right? So that's why we are further considering these four assumptions to make it your fast decoupled method more and more faster. So this is the theoretical concept of fast decoupled method. Only two equations we can solve very fast. We can converge the matrix. Now it's the comparison between our three methods, Gauss-Seidel, Newton-Raphson and fast decoupled. The first comparison is the number of iterations in the Gauss-Seidel method to reach the convergence is more, whereas in NR method the required number of iterations are less. It's a very low value, but it is very complicated. Also, fast decoupled method also the number of iterations may be less, but it's a little bit more than your NR method. But compared to GS, it is less. The computation time per iteration is very less because it is a very simple method. GS having very flat equation, very simple method, so that the time required per iteration is very less. But the computation time required per iteration in NR method is enormously high because it is a very complicated process. Whereas in fast decoupled method, the computation time per iteration is also less because we have simplified in fast decoupled method. It is a linear convergence characteristics, it is a quadratic convergence characteristics. So there is no very fast convergence here, there is no meaning of convergence. The number of iterations required for convergence increases with the size of the system. When the size increases, the number of iterations also increases in Gauss-Seidel method. The number of iterations are independent of the size of the system in NR method. So here also the same, the number of iterations does not depend on the size of the system in fast decoupled method. So the memory required is less because there is no complicated matrices in Gauss-Seidel method, so that the memory required is less. Whereas in NR method, there is a Jacobian matrix and more complicated calculations, the memory requirement is more. So whereas in the less memory is required because of the some part of the Jacobian matrix we are neglecting and we are making a system fast. So that's why the less memory requirement is there in NR method. So thank you very much for your concentration, and we'll keep continuing the examples in the next video of fast decoupled method. Thank you.